So that brings us to the Transmission Control Protocol, TCP. We talked about UDP in the last lecture. In this lecture, we're going to talk about TCP, the Transmission Control Protocol. UDP, I joked, was the unreliable data protocol. TCP is a reliable protocol. It attempts to guarantee that it will deliver all data that you ask it to send, or it will at least tell you if it didn't do that. And so you can count on it, and typically does a very good job of that. So it has all kinds of mechanisms in it for keeping track of the data that was sent, how much data has been sent, how much data has been received, how much data has been acknowledged, have we lost any data. It uses counters on data sent, it uses counters on acknowledgement, it also uses counters on how long, how it keeps track of the round trip time. It does a lot of tracking of data just to keep track of what's happening. It uses what's called a go back N form, and we talked about this briefly about 3 or 4 weeks ago. And I'm going to draw something on here real quick. So, oops, I've got to get my pen up. There it is. Take a red one, please. So let's say that you have some data that you're going to send from byte 10 all the way up to byte 1000. And so, by the way, this is a byte-oriented protocol, so it keeps track of the bytes. It doesn't keep track of how many messages you send. It actually counts each individual byte. And so let's say that you sent a block that went up to 50, and a block that went up to 100, and another block that went up to 150. And the far end received this second and third block, but did not receive this first block. Now, classic TCP will recognize that it's this middle block, this first block from 10 to 50 that I'm circling in a black circle here, that's the part that went missing. And you would think, well, it would be efficient if he only sent that bit of data that was lost. But what he will actually do is he will back up and resend all the data from the first byte that was lost. And that's just his kind of simple way to keep track of it. If he was only going to fill in the block that was missing, that would be called a selective retransmission protocol, but TCP doesn't do that. Now modern TCP does have some mechanisms to try to achieve that, but we're basically talking about classical TCP here. So in addition to this go back in, we also note that TCP is a point-to-point protocol. TCP never does a single point to multi-points, and that's part of the nature of the protocol. The protocol keeps track of the bytes going in both directions, and if he had a stream going to 3 different destinations, he would have to keep track of 3 different data streams, and TCP won't do that. TCP basically says, sorry, I'm only going to keep track of one-to-one connection communication. And so keep that in mind. You cannot, that's a laser pointer, don't want that. Don't want a highlighter, I want a pen. All right. Another thing that TCP does, since it's keeping track of all the bytes that have been transferred, it can also begin to sense when the network is congested, when it's really busy. It can sense that because it knows how long it took the data to go and get an acknowledgement back, and it also can sense it because if he loses data, he sort of assumes that there are some problems. And so TCP tries to be a good citizen. It tries to slow down if it senses that the network is congested. And so in order to slow down, he has to have some mechanisms in place to control how fast the data is going to be transmitted. And so there are these 2 things here. One is congestion control and the other is flow control. Congestion control is TCP's attempt to respond to perceived congestion by going slower. Flow control is the act of controlling how fast that data is actually transmitted into the network. So flow control is used in order to affect congestion. This works in both directions, and TCP is a bidirectional protocol, and as we'll see in just a second, it's also connection oriented. TCP will attempt to set up a connection. You can't just send TCP data from a source to a destination unless they've both agreed to talk to each other, because they have to keep track of the byte numbers and who was the last one to talk and whose turn is it. And you can kind of see, here's the header. Remember the UDP header had 8 bytes in it. TCP has a lot more bytes in it. Now we do see the classic source and destination port here. There's the source, there's the destination, but we also see this sequence number. And the sequence number is let's say I've transmitted 150,000 bytes, and the next one I'm about to send is 150,001. then the sequence number will be, here's our data down here. The sequence number will be the number of the very first byte. I'm coloring it in down here. 150,001. It'll be the number of the first byte in this bunch of bytes that are being sent. Okay? There's also an acknowledgement number. Both ends constantly send acknowledgments to each other, and every time you send a packet, you have to send the acknowledgement of the last byte that you received. And you do that by saying, the next byte I expect you to send me is, say, 75. So let's say the last byte you received was 74. Your ACK, boy, this is really bad, is going to be 75. So the acknowledgement is not the last byte I just received. The acknowledgement is the next byte I expect to see. Right? That's very important to keep in mind. Finally, there are some fields in here, and we're not going to particularly worry about those. We'll worry about the reset, synchronization, and finish fields in just a second. Now, this receive window is really important. If you are a receiver of data, you know how much memory you have. You know how much memory you have that you can set aside for data coming in. So you get to declare to the other side, hey, this is the amount of data that you can send me without an acknowledgement. And the other side has to honor that. If the other side doesn't honor that, then it could send you too much data and overflow your buffer. So if A and B are talking and A tells B, my receive window is 10,000 bytes, B cannot send more than 10,000 bytes without receiving an acknowledgement for some of that data. Of course, here we see our typical checksum again. We see one of the principles that every protocol header has some sort of error checking in it. And this urgent data pointer basically is a way of telling the remote end, hey, there's some really important data in here. It needs to be delivered in a timely fashion. And then you can set up some options. And for this course, we're not going to worry about those options. So there is your TCP header. And now let's talk about sequence numbers and ACK. Sequence numbers are the sequential number in the stream of the first byte of data in the data portion of the packet. And I mentioned that when we looked at the header just now. The ACK numbers are the next byte expected. And these are what are called, there are cumulative acknowledgments. So let's say that A and B are talking, and A sends 3 packets, and they are numbered from 1 to 50, 51 to 100, and 101 is the first byte, and the last byte is 151. And they all arrive, and they arrive really quickly. And before B can do anything, they're in memory, and he knows he has them. He does not have to acknowledge each one. In other words, if only this first one arrived, 1 to 50, here's 1 to 50, and it arrives all by itself, then B will send an ACK, and the ACK will equal 51, because that's the next byte he receives. But if all 3 of these, let's get a highlighter up here, all 3 of these arrive at the same time, essentially just within microseconds of each other, then what's going to happen is B is going to send back an acknowledgement of 152. Let's see, did I do that right? Let's see, 100 to 150. This should be 150. And this ACK would be 151. If they all arrive very quickly, he doesn't acknowledge all of them. He can send a single acknowledgement. It's a cumulative acknowledgement. It says, hey, because I'm acknowledging 151, you can know that I've received 1 through 50, 51 through 100, and 101 through 150. So that's what we mean when we say this is a cumulative acknowledgement. All right, so let's talk about how you establish the connection. It is a full duplex connection, works in both ways. It is point-to-point, not point-to-multipoint. And so we have A and B here. And these guys, what A does is he sends a request to B that says, hey, I would like to have a TCP conversation with you. I would like to synchronize, and in a religious context, this is kind of funny, but he actually sends him a SYN packet, a synchronization packet. If B is willing to have the conversation, then he sends, hey, that was kind of interesting. He sends, let's go back. He sends an acknowledgement to say, yes, I'm willing to talk to you, and the parameters that you proposed are fine. Now, but he also sends, oh, this is awful. He also sends a synchronization, so they each have to send their own synchronization, and then B will send back an acknowledgement of, A will send back an acknowledgement of B's synchronization. And so we have what's called a 3-way handshake. A sends a synchronization, B sends a synchronization and acknowledges A synchronization, and A finally acknowledges B synchronization. And what they're doing in this is they are exchanging window sizes. They're telling each other, I'm going to start at this byte. They usually start at byte 0, but they go ahead and tell each other to make sure they're both on the same page. And they initialize their acknowledgments to each other. So if A sends no data, in other words, 0 bytes, then B's ACK is going to equal 1, because the next byte he expects to see is the first byte of data. And if B sends no data, only header information, then the ACK that A sends will be 1, and A and B will be on the same page in terms of their synchronization of their byte counters. This establishes their buffer sizes, their initial byte stream parameters. And now we kind of have to talk about what are all the variables that have to be tracked in order to do this transmission. Well, each side has to keep track of the window size, so they each advertise to each other. This is how much, how big the window can be. They also have to send each other, hey, they have to keep track of the last byte that they sent, because if something gets lost, then they have to back up and retransmit all that data. They also have to keep track of the last byte they received from the other side and the last acknowledgement they sent. They also have to keep track of the last acknowledgement they received. They have to keep track of the receive window that the other side is telling them. In other words, how much data can they send. And we'll look at this one in more detail later, but they also have to keep track of what's called a congestion window, which is controlled by the sender and his interpretation of how busy the network is. They also have to keep track of something called a threshold, and they have to keep sort of a running estimate of what is the average round trip time, which they use to determine whether or not they should declare a timeout. And here's how they do the round trip time. It's an exponential weighted moving average. And if they send data and receive back and it takes 73 milliseconds, then on the first one they just go, okay, the average time is 73 milliseconds. Then on the next one they say, hey, let's say the second time they send data, it was 100. So that's where this formula comes in right now. Alpha is going to be 0.125. And so they take their estimate, which they said the first time was 73. They multiply it times 1 minus 0.125. And then they add the round trip time they just got, which would be 100, times the 0.125. And this would be 73 times 0.875 plus 100 times 0.125. This gives them a new estimate that includes some of the old numbers as well as the most recent one. The most recent one is not overly weighted. It's only rated at 1/8. All of the previous numbers are rated at 7/8. And so they don't over-respond, but believe it or not, the most recent estimate is still the most important one. And so they keep track of that. And then they say they use that number, which is going to be determined to figure out their timeout value, and that's down here. The round trip time that's estimated basically times 5 is what you can see there. All right, so we'll call that lecture number 2 and let it go at that.